I'm Xiaotong Yuan from Baidu Research Cognitive Computing Lab. In this talk, I'm going to introduce our work on the expansion ratio bound of hard thresholding with respect to the Mahalanobis distance. This is a joint work with Dr. Ping Li. What we study in this work is such an operator for truncating a vector W with respect to the Mahalanobis distance, which we call as Mahalanobis hard thresholding operator. Especially when A is an identity matrix, the operator reduces to the traditional hard thresholding operator, which has a closed form expression of preserving the top k entries of W. Such an operator plays an important role in analyzing the sparsity recovery performance of greedy pursuit algorithms. In general, MHT can be regarded as a projection operator that projects W onto an L0 ball with respect to the Mahalanobis distance. Unfortunately, for such a general case, MHT no longer has a closed form expression, as the operator is itself an NP-hard and non-convex optimization problem. We are particularly interested in the expansion ratio of such a non-convex projection operator for estimating the sparse vector. That is, for a given touched k-bar sparse vector W bar, we want to know how large is the ratio between these two Mahalanobis distances after and before truncation. Obviously, by definition, the ratio is no larger than 2. Unlike the convex soft thresholding operators, we cannot expect the expansion ratio of non-convex MHT to be no larger than 1. However, we do know that the ratio will be close to 1 for large enough k. Actually, in the extreme case when k equals p, the ratio is exactly 1. So a fundamental question is, can we find a bound that captures such a near non-expansive property of MHT, such that the bound approaches to 1 as k approaches to p? The key motivation comes from the mean squared error analysis of the hard thresholding pursuit method, which is popularly used for solving the sparse least squares regression problem. The HTP algorithm iterates between a truncated gradient descent step and a deBisson step that minimizes loss over the current supporting set. So far, the sparsity recovery guarantees on HTP are mostly about the objective value suboptimality and the parameter estimation error. In the meanwhile, the mean squared error is often considered as the prediction performance measurement of a sparse vector. For example, the MSE bound of the L0 estimator has long been known like in this form. However, it still remains an open issue if such an MSE bound can be extended to the HTP method that approximately solves the L0 estimator. The MHT expansion ratio bound turns out to be a powerful tool for bridging this gap. Here is an overview of our contributions. The theoretical contribution of this work includes a set of near non-expansive bounds for the exact MHT and its approximate variant estimated by HTP as well. Based on these bounds, we are able to establish a mean squared error bound of HTP algorithm for compressed sensing problems. For algorithm development, we also contribute a novel preconditioning extension of HTP, which has a provable MSE guarantees and a superior actual computational performance than the plain HTP. The expansion bounds of hard thresholding operators have received recent attention for recondition-free analysis of HTP-style methods for sparsity recovery. An HT suboptimality bound has been derived by Zheng et al., which is key to establishing rip-free bounds for high-dimensional sparsity recovery. Later, a dimension-free bound of HTP has been essentially independently established by these two groups of researchers. Such a nearly non-expansive estimation error bound has been demonstrated to be beneficial for analyzing the parameter estimation and the sparsity recovery accuracy of HT type methods without assuming RIP conditions. Despite the remarkable success, these results are mostly relevant to the objective value suboptimality and parameter estimation accuracy. In contrast, the theoretical understanding of the MHT operator yet still remains an open issue that we aim to study in this paper. We start by presenting a key lemma that plays a fundamental role in showing the expansion ratio bound of MHT. Suppose that we have a k-sparse vector U, which is somehow computed from W. The lemma basically says that if U satisfies the conditions A and B, and K is sufficiently larger than bar K as indicated in condition C, then the expansion ratio of U with respect to W can be bounded like this. We would like to talk a little bit about the proof. The main idea is to first bound this difference term from above based on the orthogonal condition A. And then we bound this term from below using the strong signal condition B. In view of this lemma, we can easily establish an expansion ratio bound for MHT, assuming that it is exactly known. Actually, in this ideal case, we can show that the MHT operator satisfies these two first-order optimality conditions, which are exactly what the lemma requires. And of course, we always have the expansion ratio is no larger than 2. Since MHT is an NP-hard combinatorial optimization problem, it will be more realistic to study its polynomial time approximated estimators. To this end, we consider the setting where MHT is approximately optimized by HTP method. The good news here is that after sufficient iteration, the HTP estimation of MHT also satisfies the following two conditions, and thus the key lemma can be substantialized to this case to obtain an almost identical near non-expansive bound to the exact case. Now equipped with expansion ratio bound of MHT, we are able to analyze the mean squared error performance of HTP method for sparse least squares regression. Actually, up to sparsity level relaxation, the bound nearly matches the MSE lower bound of Zhang et al. For polynomial time sparse linear regression estimators. Okay, let's move to talk about the algorithm. We have developed a preconditioning HTP method. The main idea is to sample a random RID subset of data to form F tilde as a stochastic approximation to the full objective function. F tilde actually serves as a preconditioner for Newton type optimization procedure. The iteration loop of our method is as follows. We first construct a quadratic function based on F tilde and the global gradient at the previous iterate. And then we solve it under the same sparsity constraint to update the next estimator. To justify the preconditioning effect, we can see that without sparsity constraint, the update procedure can be compactly expressed in this form. This clearly shows that F tilde serves as a preconditioner for a Newton type optimization procedure. For MSE analysis, we can show this bound provided that F tilde is sufficiently close to the full objective function F. The bound matches that of HTP under proper setting of subsample size M and gamma. Concerning the computational complexity, if using conjugate gradient method, to solve the quadratic subproblems involved in the debiasing steps, we can show that the preconditioning HTP is substantially cheaper than HTP in computation when the sample size n is sufficiently larger than the sparsity level k. Now let's verify the expansion ratio bound of MHT estimated by HTP through a numerical study. As we can see, the bound has dependence on the condition number of A and the sparsity level k. We test with a dense vector W constructed like this, where the W prime bar is a k bar sparse vector orthogonal to W bar. We fix P equals 1000 and k bar equals 200 and test how the expansion ratio evolves on the different metric A with varying condition numbers. From this set of results, we can see that for each fixed matrix A, the expansion ratio of MHT is relatively large and k is relatively small, and the ratio converges to 1 as k approaches to P. And also, for each fixed sparsity level k, the expansion ratio grows larger as the condition number kappa increases. These numerical evidences will support the theoretical prediction. We now turn to evaluate the computational efficiency of the proposed preconditioning HTP method for estimating the sparse least squares regression model. We test with P equals 10,000 and k bar equals 100. We evaluate the MSE performance of preconditioning HTP under varying subset sample size M and take the plain HTP as a baseline for comparison. The results for n equals P and n equals 4P are shown in this figure. From this group of results, we can observe that the preconditioning HTP is consistently faster than the plain HTP in MSE convergence, and the margin becomes more significant for relatively larger sample size. And for each considered sample size n, the most efficient implementation of preconditioning HTP occurs when using relatively smaller subset size m. These observations are consistent with our theoretical analysis. To summarize, in this work, we present a set of near non-expansive bounds for MHT and its HTP estimation as well. Based on these bounds, we provide an MSE analysis of HTP that nearly matches the lower bound for polynomial time sparse linear regression estimators. Also, we propose a preconditioning variant of HTP which has near optimal MSE guarantees and exhibits superior computational efficiency than vanilla HTP. Here are the references. That's the end of my talk today, and thank you very much for your attention.